Okay, let's go ahead and figure out the work done in emptying this tank. We're going to pump the water out right out the top, so right out here. The acronym that we use is that work is equal to the integral of ADD volume. So this acronym works very nicely as long as we know what everything stands for. So the A stands for acceleration due to gravity, so that will be 9.8. And then this D stands for density, so that's the density of the liquid that's in the tank, and we are dealing with water, so the density is 1,000. And then D, the second D stands for distance traveled. So let's draw a representative cross-section. There is our representative cross-section at a random y. And the distance that that cross-section has to travel to get out of the tank is going to be 9 minus y. The full tank is 9 high, and our cross-section is y high, so it will travel 9 minus y to get out the top of the tank. So there's our ADD. And now volume, we have to be careful here. Volume means the volume of a slice. So we imagine our cross-section having some thickness. And that thickness is going to be dy. That volume is what goes into the integral next. So the volume there, we have a cross-sectional area of pi times the radius squared, and then we have to multiply by that thickness, which is dy. So that right there is the volume of a slice. Remember that a slice is three-dimensional where a cross-section is only two-dimensional. So the pi times r squared is the area of a cross-section. And then the volume of the slice we multiply by dy. Now this integral is going to be from 0 to 9. And now we just have to do some math here. We're going to pull out the 9,800. We can pull out the 9 pi. And then all that we have remaining is the integral of 9 minus y dy. And then 9,800 times 9 is 88,200. That's multiplied by pi. And then we will integrate here using our power rule. 0 to 9. Plugging in 0, that's not a contributor, so we can kind of ignore that. Plugging in the 9 will give us 81 minus 81 halves. Whoops, that's going to be a 2 down there. So 81 minus 81 halves. Well, that's going to be 81 halves. Let's come up here. So we're going to have 88,200 pi multiplied by 81 halves. And that is going to give us a bunch of joules. We will, when we multiply those constants together, we'll leave the pi alone. If we wanted a rounded answer, we would, replace pi with 3.14 or something. So there are those. That's how many joules it takes to empty the tank out the top. Now, to empty the tank, if we wanted to empty it out the bottom, it would be the same. The only difference would be that emptying out the bottom, gravity is doing the work, whereas emptying out the top, a pump is doing the work. Okay, and those are going to be equivalent in this case, same amount of work, because the tank is symmetric. If we had something like a cone where the top half of the tank is different than the bottom half of the tank, then we would not have the same work done pumping out the top and out the bottom. So a cylinder is symmetric in a way that the work would be equal. Now part B here says, is it true that it takes half as much work to pump the water out of the tank when it's half full? And the answer is no. If we look at our tank, if we had the just the bottom half of the tank filled, so let's suppose we're thinking about the bottom half here, this half of the tank has to travel much further than the top half of the tank, right? So that the average slice in the bottom half of the tank is going to travel further than the average slice in the top half of the tank. So we will not get half of the work that we found in part A. Now we could easily figure out how much work it does take, and the only difference is that our integral is going to look identical. The only difference is going to be our limits of integration. Our limits of integration are going to be 0 to 4.5. Everything else in here is going to be the same all the way through. So to figure out how much work it takes to empty out half a tank, just compute that.